Thanks for sticking through the session. This time I'm presenting you Reverie. In this work, we actually tackle the buffer sharing problem in the specific context of data centers that serve RDMA and TCP together. This is a joint work with Wei from Microsoft, Stefan, my supervisor from TU Berlin, and Maria Apostolaki from Princeton. So, yeah. Traditional data center networking involves TCP-based applications. The host networking actually consumes quite a lot of CPU clock cycles. Traffic is in general loss tolerant in traditional data center networks. Modern data center networks are slightly different. They are mostly applications based on RDMA. Host networking is fully offloaded to the network interface card that implements the entire networking stack. Traffic is specifically lossless, and this requires something called priority flow control. In production, there is a mix of RDMA and TCP applications together. Switches use shared buffers, and RDMA TCP actually share the same common buffer space at each hop in the network. Let's see how this works out with just TCP from buffer sharing point of view. There is a switch with a shared buffer used by some input ports and output ports. We have a TCP flow coming in from two input ports. Packets queue up in the egress queue. As the queue length increases, the buffer sharing algorithm takes packet drop actions depending upon the egress queue lengths. So buffer sharing with TCP involves egress queue lengths, and the action is packet drops. A buffer sharing algorithm typically assigns thresholds for each queue, and a packet is either accepted or dropped depending on the queue length versus threshold, how far they are from. With RDMA, this is slightly different. The same example, packets are coming in, but this time these are RDMA flows. They are coming in from two input ports, and packets queue up in the ingress. A buffer sharing algorithm actually looks at ingress queue lengths this time, and as the queue length grows, the action is different. Packets cannot be dropped. A PFC pause is triggered at this point. As the queue length decreases, a PFC resume is sent back. So in essence, RDMA buffer sharing relies on ingress queue lengths, and the action is PFC. The buffer sharing algorithm assigns thresholds similar to the case of TCP, but now on the ingress queues. Packets are always accepted, but depending upon the thresholds, a PFC pause is triggered. When these two types of traffic with very diverse needs intersect at a common shared buffer, very interesting problems arise. They interact in a very harmful way, leading to unfair buffer allocations across these two traffic types, eventually leading to very poor burst absorption. Much of this paper, we start to understand why such problems arise, and we dig into the sonic buffer model, which is widely deployed across many switch vendors. So here we're looking at a single piece of buffer. Sonic views this buffer piece in two different views, from the ingress perspective and from the egress perspective. Every packet is accounted twice, once in the ingress, once in the egress. The buffer is further logically divided into so-called pools. In the ingress, there is an ingress shared pool, which is shared across RDMA and TCP. There's a headroom pool that is dedicated for RDMA. In the ingress, we have two pools for RDMA and TCP. So that's the sonic buffer architecture. We still don't know exactly why it exists this way, but it was engineered this way. In this work, we do the first analysis of this complex architecture, and we find three interesting problems. Let's see how RDMA packets are accounted in this architecture first. Packets are coming in. They occupy space in the ingress shared pool as well as in the egress shared pool. Packet is accounted twice. Same goes with TCP packets. Packets come in, they occupy the shared pool with RDMA in the ingress. They occupy their own dedicated pool in the egress. Packet is accounted twice again. In each pool, the admission control is such that it implements dynamic thresholds, which is a well-known algorithm in the buffer sharing context. Dynamic thresholds is essentially a function of the remaining pool size, a constant factor of it, which is configurable. Without going into much details of SONiC, let me show you the interesting problems that arise in this architecture. First, we find that TCP actually gets much more buffer than RDMA, although the configuration is intended otherwise. Here we're looking at the number of queues of TCP using buffer on the x-axis, number of queues of RDMA using buffer on the y-axis. Color indicates the ratio of buffer allocated to each of these types. As we see, a fair allocation cannot be achieved unless the number of queues of TCP are very small. This is the first problem. The second one is even more interesting. A PFC pause gets triggered because of TCP's occupancy. Remember, PFC pause was the control signal for RDMA. So here we are looking at number of RDMA queues on the X, number of TCP queues on the Y. On the Z-axis, we are looking at the PFC thresholds. As TCP queues consume more and more buffer, RDMA's PFC pause threshold gets drastically affected. Even more interestingly, TCP's drop thresholds actually don't get affected because of RDMA, which is surprising because we want to usually prioritize RDMA lossless traffic in the buffer, whereas SONiC buffer model turns out, it looks like it supports TCP much more than RDMA. Finally, why does burst absorption suffer in this architecture? We dig into this and find that the culprit here is the instantaneous queue length, which actually fluctuates quite a lot because of the traffic pattern. Thresholds are a function of queue lengths and the buffer occupancy, which also fluctuate a lot. And the whole admission control essentially overreacts to these transient changes in the buffer. Based on these observations, we designed Reverie to answer isolation as well as burst absorption for both RDMA and TCP together. What we do is merge this entire complex architecture into a shared pool, a single shared pool for RDMA and TCP. We merge all the pools into one shared pool for RDMA and TCP, a headroom pool dedicated for RDMA, which is for a special purpose. Within the shared pool, we basically consolidate the ingress and egress views of SONiC, which gives Reverie a bird's eye view of the actual buffer content. Every packet is only accounted once, in contrast to SONiC, which accounts twice in ingress and egress. For RDMA, Reverie accounts a packet from the perspective of ingress queue. For TCP, we account it from the perspective of egress queue only. The split and the allocation between RDMA and TCP is basically governed by the thresholds used in Reverie. And the thresholds we use are similar to prior work, which is also our own work from ABM. The ideas carry on from there. We use a constant factor alpha, which is configurable. For instance, you can configure one alpha value for RDMA, one alpha value for TCP, which gets multiplied by the remaining pool size. In this case, we only have one pool, and the reciprocal of the number of congested queues for each type of traffic. Essentially, this gives us both the desired properties of isolation and fair allocation across different traffic types. We give formal proofs in the paper. Please have a look at it. The final piece of the problem, how do we improve burst absorption when RDMA and TCP traffic interact together? In this case, we introduce the notion of low-pass filter-based admission control. instead of overreacting to every transient state of the buffer, what we do is pass the Q length through a low-pass filter, and we compare thresholds with the low-pass filtered Q length. This allows Reverie to smoothly react to the transient state of the buffer. In the paper, we have much more interesting details on, mostly from the formal point of view, how we achieve fair allocation, how we improve burst absorption. We give formal proofs. Please have a look at the paper for these details. For the evaluation, we use NS3 packet level simulator, and we use a 256 server topology, 3-stage close with 4 spine, 16 TOR switches. Every server is equipped with 25 Gbps NICs. We use the well-known web search workload obtained from real-world data center networks. On top of that, we superimpose this workload with a synthetic incast workload to stress the buffer even more. Each switch implements a shared buffer, and we use dynamic thresholds and ABM both from prior works in the sonic model, and we compare these two algorithms with Reverie. First, we are interested mainly in whether Reverie reduces the interactions between RDMA and TCP. For this, we do the experiment where we vary the TCP load. Here on the x-axis from left to right, the TCP's load on the buffer is increasing. On the y-axis, we are actually looking at what's happening with RDMA traffic in terms of PFC pauses. The lower, the better. As we see, TCP's load affects less when using Reverie. When using dynamic thresholds and ABM, both the prior works, TCP's load drastically impacts RDMA's traffic in terms of PFC pauses. Next, we look at how burst absorption of RDMA is affected by TCP's load. The same type of plot here. On the x-axis, the load of TCP is increasing. On the y-axis, we are looking at the flow completion times of RDMA incast flows. The lower, the better again. As we see, Reverie is almost unaffected by TCP's load, whereas ABM and dynamic thresholds significantly suffer as TCP's load increases. We see whether we can still improve prior works if we can provision them with a larger proportion of TCP's, larger proportion of buffer towards TCP. On the x-axis, we are increasing TCP's pool size for DT and ABM. On the left, we are looking at the performance of RDMA. On the right is the performance of TCP. Both the existing algorithms can either perform well for RDMA or for TCP, but not both together. There's no good sweet spot. In contrast, Reverie performs consistently for both RDMA and TCP. In conclusion, existing sonic model with different admission controls cannot serve the diverse needs of RDMA and TCP together. We show these problems also formally in the paper. We designed Reverie that achieves the desired goals of isolation as well as burst absorption for both types of traffic. We also show this allows us to improve flow completion times for both RDMA and TCP together. Finally, the source code is also available on GitHub, and I'm open for any questions now.